We will get started with Chapter 11. Chapter 11 and Chapter 12, they both deal with the notion of risk and return in capital markets. When we invest in any investment choice that we have, a stock or a bond, for example, we invest anticipating a return on our investment, meaning that if we invest a sum of money today, I'm expecting that at some period in the future, I'm going to get something more than what I invested. And in the interim, I may be paid some dividends. Maybe, doesn't have to be, but I may receive some dividends. If this was a bond, I'm investing in a bond, I'm expecting to receive the principal back of the bond at the end of the bond's life, and in the interim, I would be paid interest payments. So whenever we invest, we're investing with the promise of a return. And return, we generally calculate return in a simple exercise like this. It'll be PT minus P0 divided by P0, assuming there is no dividends. If I assume no dividends, then that would be what my return would look like. Just the difference between the two stock prices divided by the original stock price. So the easiest way to remember the equation for return is that ending stock price minus beginning stock price divided by ending stock price. So whenever we invest with a promise, with an expectation that we will receive a reward. That's easy. That's easy to understand that that's our expectation. Why else would we give up our money today if I don't have expectation of getting something more than what I'm giving up today, tomorrow? The harder question is the notion of risk. Because if you think about a simple stock investment, we are investing P0 today. This in price that we are expecting in the future is not guaranteed. We have a notion, an expectation of what it may be, but we are in no way guaranteed that we will receive this sum of money. That means this promise of a return comes with some associated risk. Some associated chance that we may not get what we are being promised. So that chance that we may not get what we are being promised is what we classify as risk. Anytime anything deviates from our expectation, we think about it as a risky venture. When it meets our expectation, then we expect that there is, we do not think about it as risky. But risk is anytime it deviates from expected norms. So within capital markets, investments have to be judged not only on the basis of their return, which is the obvious one, but the less obvious one is also on the basis of their risk. So in Chapter 11, what we are trying to do is first come up with definitions of risk and return, and number two, begin to look at what happens when we combine stocks or bonds or any risky investments into portfolios. A portfolio is a collection of assets that I have invested in. Instead of investing in one asset, I've invested in a collection of assets. So let's take a look at this. So we start by looking at what has been the historic performance of different investment choices between 1929 and 2012. So, and the way we do this is we start by looking at $100 that we had invested in 1929. So in 1929, we had invested $100 in each of these choices. We invested $100 in the S&P 500 index, in a portfolio of small stocks, in a portfolio of global stocks, a portfolio of corporate bonds, and a portfolio of treasury bills. All of these are portfolios, meaning we're not just investing in any one stock. In the small stock universe, we are investing in a multitude of small stocks in one portfolio. So we invest $100, and then we track their movements over time. So the red line tracks for us how the $100 invested in small stocks have done over time, and we see that by the time we get to 2012, that $100 investment in small stocks had grown to 3,221,000 approximately. The same $100 investment in S&P 500, which is generally viewed as large stocks, large cap stocks, that would grow to 319,000. And the same $100 investment in, say, corporate bonds would grow to only 21,000. And had you invested in treasury bill, that would have grown to 2,042. So there is an obvious difference in these numbers. And from this, we can also compute returns if you wanted to. You can take that ending value minus the initial value, divide that by the initial value. That will give you the return on that $100 over, that would be over 83 years, approximately 83 years. And of course, we see that there is a difference in our ending wealth, which means there is a difference in the returns we get from each of these choices. Now, given what you know from this slide over here, would you then necessarily conclude that investing in small stocks, in small cap stocks, is the way to go? Since it has the highest return, is that the way to go? And the answer is you probably cannot answer that, because we only have one piece of information. What we are lacking at this point is what is the riskiness of investing in small cap versus large cap versus bonds versus treasuries. What is the risk? That's not obvious. We do not have a metric yet, and it's not obvious what that answer is. But we do have some hints. If you look at the squiggly line that tracks the small cap stock, the red line that tracks the small cap stock, you see that it is much more volatile. It is doing this. It is moving up and down much more than, say, compared to the yellow line, which is kind of doing like this. So this volatility, this picture, is more volatile than this one, which means the red line is much more volatile than the yellow line. And the red is more volatile than the blue is more volatile than the black is more volatile than the yellow, and so on and so forth. How am I coming to that point? Because there is much more deviation, much more changes in the value, much more deviation in the value in the red compared to, let's say, the yellow. So that's how I'm concluding that the small cap stock is much more volatile than the corporate bond, for example. But what we do not have, even if we can come to that conclusion, I still cannot answer the question, is this investment a worthy choice? Is that the choice I would always choose? In short, I know the answer. That's not always going to be the right choice, because if everybody chose small cap stocks, then of course these investment choices would not exist. The fact that there is a robust market for treasury bonds, there's a robust market for corporate bonds, for large cap stocks, tells you that Of course, all investors will not choose small cap stocks. So the question is, when should we choose and when should we not choose those kind of stocks? And the only way to answer that would be to much more formally define risk and return. So the first thing we want to define is return. In a simple one period timeline, 0 being today, 1 being tomorrow, or in general you can say this is t and this is t plus 1. So this is t and this is t plus 1. So the return over this time period would be the return over the period t plus 1. Okay. And that return will depend upon what is the price of the stock today, what is the price of the stock one period from today, and what is any dividend payment that happened over that one period. So the gains in my cash comes here, subtract that from the initial, divide that by the initial. So again, you can look at this as end minus begin, divide by begin. I had made a mistake over here. I just realized this should have been begin, not end. P0 is begin. Okay, so now if I take this equation and just break it down into its component parts, so I take PT and I divide that into this and the sum of these two. So I have dividends divided by P plus P1. The way I would write this is D divided by P0 plus P1 minus P0 divided by P0. So D divided by P0, that's my dividend yield, because it is measuring the percentage of dividend relative to the stock price today. And P1 minus P0 divided by P0, that would be capital gains yield. That's the return that is coming from the rise in the stock price, and the rise in the ending stock price. So this is one way to look at one period returns. What if you had multiple periods? For example, 2 periods. So the stock price today is P0. This is period 1, period 2. Stock price at the end of period 2 is P2. Dividends over that time is D1. Dividends over that period is D2. Then return over this period, the return over this entire period would be ending stock price minus beginning stock price plus D1 plus D2, both dividends, divided by P0. And this return is also often described as the holding period return. The return that I have received, the reward that I have received from my investment over the period that I have been holding, my return. So if I take this equation and I want to generalize this, so today, future D, and there are many, many periods between today and future T. Stock price today is P0. Stock price at some period T in the future is PT. and there are multiple dividends being paid over these periods. So there is D1, D2, and then dot, 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 all the way. I'm being paid multiple dividends. Each year I'm being paid a dividend. 1, 2, dot, 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 all the way till T. In this case, holding period return, which is my reward from investing, would be ending stock price PT minus beginning stock price P0 plus the sum. This is the summation of all dividends. I add up all of the dividends, and the way I write the summation sign is I put I, and then I put I equal 1 to T, meaning I'm adding up. So when I takes the value of 1, D1. When I takes the value of 2, it's D2. In essence, I'm adding up all of these dividends. Simple sum of all of these dividends. And then I divide this by P0, the beginning stock price. So that's my reward calculation. So here is a quick example. Microsoft announced a special dividend of $3.08. You bought the stock at 28 and sold it immediately after the dividend was paid at 27.39. What's your realized holding period return? So you bought the stock at 28.08. The stock paid a dividend of 3.08, and you sold it immediately after that at 27.39. So what's your return over that period? It's the dividend plus the ending stock price minus the beginning stock price, the whole thing divided by the beginning stock price, and that'll give you 8.51%. If you want to divide this into its components, if you want to figure out this 8.5% reward that you received, what proportion of that came from dividends and what proportion came from the rise, or in this case, the fall in stock price. So dividend yield would be the dividend divided by the stock price. If there were multiple dividends, we will just simply add up all of those dividends. But in this case, dividend divided by the stock price, since there's only one dividend, which shows that 10.97% of your return was driven through dividend yield. And then I look at the ending stock price minus the beginning stock price divided by the beginning stock price. And in my capital gains yield, I lost 2.46%. So if I add 10.97, in this case, minus 2.46, I would get 8.51. So this is useful for several reasons, to break down overall return into the two components of dividend yield and capital gains yield. It is useful for one reason. It is that it gives us a look into what is the source of my reward. Where is my reward coming from? That's useful. And the second usefulness is that it is based on taxation, because sometimes, depending upon the tax code, dividends are taxed differently than capital gains. It has been historically in our tax code that capital gains has historically been taxed at a lower rate than dividends. If that's the case, then investors would like to see more of their return coming from capital gains than from dividend yield. But if the taxation on dividend and taxation on capital gains is the same rate, then investors would be indifferent between where their return comes from. But if dividends and capital gains are taxed differently, then investors will care about where their returns come from. Okay. You can practice some of these other problems, very similar problems, review them. So now let's look at compounding. So typically when we think about returns, Sometimes we view returns, for example, in quarterly increments. For one reason is because dividends are paid quarterly. So we can look at returns in quarterly increments. And then from that, what we need to find out is what is my annual return, or in this case, what we would call annualized return. What do these returns annualize to? And the way we calculate that annual return is we take the product of what we call the wealth relatives. We take each quarterly return, add 1 to it, and then take the product of all four, and 1 plus, that gives us 1 plus the annual return. So take an example like here. Microsoft has these stock prices available to us historically, and these are the dividends that Microsoft has paid over time. How do we calculate? What is the annual return for Microsoft in this case? Okay. So to do this, based on each price, I will compute return. So this return is calculated as ending price 27.39 minus beginning price 28.08. So this is the ending price, this is the beginning price, plus the dividend 3.08 divided by the beginning price 28.08. That will give me 8.59%. This next one would be calculated as ending price is now 25.93 minus 27.39 plus the dividend, which is now 0.08. I divide that by the beginning price, 27.39. So each of these returns are calculated based on this is end, this is beginning for this time period. However, for this time period, this is end and this is beginning. And we repeat that. So now I have a distribution of my returns from November 1 to October 31st. Okay, so I have 5 observations over here. Then what do? I take the 5 returns, add 1 to them, and I multiply each. So the first one was 8.51, so this is 1 plus 0.0851. This one would be 1 minus 0.0504, and so on and so forth. Then I multiply everything, subtract 1, that gives me my annual return for that 12 calendar month. This annual return is also called annual realized return. As over here, same question, asked a little bit differently. What was your realized return over that one year period? Same thing, you will engage in the same process. You have price, you have dividends, you will convert them into returns, a return series like this, and then you will multiply everything over that 12-month period. So that gives us a 1-year return by compounding. In other words, if I have periodic returns, I can calculate the annual return from those periodic returns as long as I have a data period that spans the whole year, as over here. It goes from March to March. So that's a 12-month period over which I have the data. I can then calculate the annual return or my 1-year return. This 1 year return does not have to be the exact 1 year in terms of a calendar, but it has to span the 12 months. Okay. Similarly, you can practice some of these other problems. Now, when we look at a series like this, we see that period by period, the returns vary. So every quarter, the stock yields different returns. So how do I then compare, for example, the return from a series like this to a return from a series over here? How do I compare them? They cannot be directly compared. Although they are both quarterly returns, they cannot be directly compared. The only way I can compare them meaningfully is if I take a look at these quarterly returns and then come up with some sort of an averaging, some sort of an average or some sort of a mean. And that's what we do next. And the way we calculate the mean is we simply add up the returns that we have for whatever number of periods. Now we are not limited to a 12-month period. We could have quarterly returns for the last 10 years. We could have monthly returns for the last 10 years. Or we could have annual returns for the last 10 years. All we have to do is add up the returns that we have observed over whatever calendar period we observed them and divide it by the number of observations that we just had. So this is the classic definition of mean or average. You add up the observation and you divide it by the number of observations you have. So that's average return or mean return. But mean does not tell us the whole story. So if you look at the average return for small stock, S&P, corporate bond, treasury, these numbers, these are now annual averages, so year by year averages. They match up to what we saw in the first slide, that the small cap stocks in general do better than the large cap stocks or corporate bonds. But that does not tell us the whole story, because in addition to looking at year by year number, what we also have to look at is the dispersion of those numbers, the variability of those numbers. And here we see that the variability of the treasury bills, they're very tight. Not a whole lot of variations. Variation of corporate bonds, somewhat wider. Variation in large cap stocks, a little bit more wider. And variation in small cap stocks, the largest. The low value going as low as minus 50% to as large as plus 100%. You don't have that range for the corporate bonds or for small cap stocks, and certainly the tightest for 1 month treasury bills. Looking at these four pictures, the green, the yellow, the blue, and the red, it should begin to tell us the story of risk. Why is small cap stocks the riskiest? Because it has the widest dispersion of numbers. That means on any given year, outcome could be as low as minus 50 to as high as plus 100 for the red bars. However, for the blue bars, they're, for example, for the yellow bars, much tighter, anywhere between, say, 0 and 30% or 40%. So a much narrower dispersion of numbers for the yellow bars versus the red bars. This tells us a story of risk. That the small cap stocks are more risky than the treasuries, the corporate bonds are more risky than treasuries, large caps are more risky than corporate bonds, and small caps are more risky than large caps. But how do we define this? Looking at a picture is one thing, but being able to define it is a whole nother thing. So how do we define risk? And one of the tools that we have to define risk is, we borrow this from statistics, just like we borrowed the idea of mean or average from statistics, is the idea of variance. And how do we calculate variance? We take the deviation of each return from its mean return. So over here, we calculated the mean. Now, we calculate the deviation of the first observation from its mean value, the second observation from its mean value, and we keep on doing it until we get to the very end. Then once we get to the very end, we go back and we start squaring each of these deviations. We take the square value of each of these deviations. And then we add everything up. After we add up all of the squared deviations, so essentially the blue box represents the sum of squared deviations from mean. Sum of squared deviations from mean. So again, let's recap the process. We take the difference between each return from its mean value. That's the deviation from mean. Then we square it, and then we add them up. Three-step process. First, the deviation from the mean, then we take the square of the deviation from the mean, and then we add it up. And we divide all of that by t minus 1. We divide the entire blue box by t minus 1. This process yields for me the variance, the variability of my distribution. Once I take the square root of the variance, I get my standard deviation. Sometimes we also write that as sigma. And standard deviation is a measure of risk. Why is standard deviation a measure of risk? Because standard deviation, if we assume that our observations are normally distributed, and generally for any large set of data, it is quite reasonable to assume that the observations that we have are normally distributed. Then the central value, the central number, represents the mean. And then around that mean value, we have +1 standard deviation, -1 standard deviation, +2 standard deviation, -2 standard deviation, +3 standard deviation, -3 standard deviation around the mean value. And once we have assumed normal distribution, we know that these ranges of value are pretty standardized. 67% of the observations will be between -1 and +1 standard deviations of the mean. 95% would be -2 +2, and 99% would be -3 +3 standard deviations above and below the mean. So then sigma gives me a measure of risk, as we will see in a moment when we put some numbers to it. So take, for example, this time series. We have the returns in each of the years from 2005 to 2009. Once I have those returns, I can calculate my mean value. So what would I do? I will add up these numbers. Mean value would be 4.9, 15.8, 5.5, -37, +26.5. This whole thing divided by 1, 2, 3, 4, 5. 5 observations. If I do that, that comes out to 3.1%. Notice what I have done. I have added all these numbers in their percentage form. I prefer that you do it that way. Although you don't have to. You could have converted this into their decimal. I think the book does it that way. And then you could have added these numbers up, divided that by 5. The answer would have been 0.031, which is the same as 3.1%. So I prefer that you develop the habit of doing this in their percentage numbers. It's just easier to compute. You don't have to worry about the placement of the decimal signs and things like that. Although there is no difference. If you prefer the other way, that's fine too. Once I have those returns, then I'm ready to calculate variance. And the way I would do this would be 4.9 minus 3.1 squared, 15.8 minus 3.1 squared. So notice what I'm doing. I'm taking each observation, subtracting the mean value, then squaring it, plus 5.5 minus 3.1 squared, plus minus 37 minus 3.1 squared, plus 26.5 minus 3.1 squared. So I add everything up. I add up all of that and I divide that by 5 minus 1. There were 5 observations. It is always t minus 1. And when I do this, I would get this as 580. If I was using percentage numbers directly, then I would get that as 580. If I'm using decimal, that would be 0.058. Once I get 580, then I take the square root of 580. That would be 24.1. If I take the square root of 0.058, that would be 0.241 or 24.1. So that's how we get standard deviation. This is my sigma. I'll interpret this in a moment, but let me take you through this table. And I suggest you use this tabular format to work out your problems from this chapter. Whenever you have to calculate standard deviations, you have the returns. Again, you could have entered them as percentages or as decimals. Either way would give you the same thing. So you have the returns. Then the next row you have averages. The next row you are taking the difference between these two. And the next row you are squaring this part. You're squaring the differences. So that way you have a template and you just have to fill in the template. Return, average, difference, square. And once I have all of the squares, I'm going to add this last row up. Add it up. When I add it up, then I divide it by the number of observations. In this case, I have 1, 2, 3, 4, 5 observations. I divide that by 5 minus 1. That gives me variance. When I take the square root of that variance, I get standard deviation. So what does that mean? What does that 3.1 and 24.1 imply? To understand that, we have to apply this in the context of a normal distribution. The mean value is 3.1. What does that mean? It means it is 3.1 plus 24.1. Right? The standard deviation was 24.1. This one is 3.1 minus 24.1. So the range is now going to be 27.2, and this would be 21. So this range of 21 to 27.2, the likelihood of these, the likelihood that a outcome would be between 21 and 27.2 is approximately 67%. The likelihood, why 67? That's just the normal, that's just the standard definition of a normal distribution. That 67% of the observations would be between plus and minus 1 standard deviation from the mean. 95% of the observations would be between plus and minus 2 standard deviations from the mean. So the 2 standard deviation plots would be, then I get 27.2 and add 24.1 to it. So this would be, this point would be 3.1 plus 2 times 24.1. So that would be 51.3. 51.3. And this point over here would be 3.1 minus 2 times 24.1. So that would be so that would be 48.2. So negative 48.2 plus 3.1. That would be 1 minus 45. Oh, this was minus. The original one was minus over here. So the 67% likelihood the distribution would be from minus 21 to plus 27.2. So the 25% would be minus 45.1. So that means there is 95% likelihood that the outcome would be between minus 45.1 and 51.3. Minus 45.1 and 51.3. So make a correction. This should have been minus. For the 67%, the range is from minus 21 to 27.2. For the 95, it is between minus 45 and 51.3. So the reason we have such wide dispersion of outcome, what is driving that? What is driving it is the high standard deviation, 24.1. Sigma is 24.1. That's a large standard deviation. If the standard deviation was smaller, instead of 24.1, let's say it was 2.1, then you can obviously see that these outcomes would be much tighter. So you can actually begin to visualize what standard deviation is doing. Standard deviation is giving me wider dispersion in outcome. The probabilities are remaining the same. This is 67% likelihood. Plus minus 2 standard deviation is 95% likelihood. So whether standard deviation is 24.1 or if I assume this to be 2.1, these likelihoods are not changing. What is changing are the outcomes over here. What these numbers would look like. What the dispersion would look like. And the dispersion is much wider, larger the standard deviation. It is for this reason standard deviation is viewed as a measure of risk. Okay. You can practice some of these other problems on your own, calculating standard deviation. Try to use the table method. It's just easier to work that. And then you can see. Now you see that the small cap stock had a large return, but it also had large standard deviation. The large cap stock has a higher return than corporate bond, but it also has higher standard deviation. So the reward, the higher reward that we had in small cap stocks versus large cap, versus corporate, versus treasuries, that larger return is driven by larger risk or greater risk. And this should make intuitive sense. If a particular investment is riskier, then what is the only way investors would invest in this riskier venture? If it provides higher returns or higher rewards. That's the only way investors would invest in riskier stocks. So now we have a much more complete picture that yes, small cap stocks are giving me higher reward than large cap or corporate, but it is also coming at a higher risk. So the question that I have to ask is the reward reflective of the risk? Is it a fair compensation for the risk? That question is slightly outside the preview of this particular chapter, and maybe also somewhat outside the preview of this particular course, but we will address that in the next chapter a little bit. But over here, at least we have completed the definition of reward and risk, how to define reward and how to define risk and measure reward and risk in a financial investment. Just a recap of the normal distribution. Average 2 times standard deviation gives me the 95% prediction interval. So 2/3 of the observations will be between 1 standard deviation up and down, 95% between 2 standard deviations up and down. So it's just recapping that and recapping what we just did in terms of figuring out the range of possibilities. Okay. You can practice against some of these other similar numerical problems, and this kind of gives you some of the a recap of the tools that you will be needing to calculate returns, risk, and interpret what that risk means. So this completes the first part of chapter 11.